So NAT64 is a transition technique. In other words, we've got this whole idea that we've got some isolated pockets of IPv6 only hosts in my network, but they're not connected directly to each other across a pure native IPv6 cloud. That there's one or more IPv4 clouds in the middle, which is blocking our native end-to-end IPv6. Now, in some of the previous videos, I've talked about some tunneling techniques like ISOTAP and 6-4 in order to take those native v6 packets and tunnel them inside of v4 headers. Well, that's fine if you've got v6 talking to v6, but what if I've got a v6 only host that needs to communicate to a v4 only host? Then tunneling won't work. In that particular case, I need to actually translate. I need something that's going to remove the v6 header and completely replace it with an IPv4 header. And conversely, when the v4 reply packet comes back, we need to remove that v4 header and replace it with a v6 header. So this is a translation technique, not a tunneling technique. Now, look at the second bullet point here. NAT64 was primarily designed to allow v6 hosts to initiate connections to v4 content. We know that right now the vast majority of web servers in the world and other servers are IPv4 servers. This video is being recorded in 2015, and that's currently the case. You know, maybe 15, 20 years from now that will flip over, but not right now. So if I actually have a v6 only host, let's say I completely remove the IPv4 protocol stack from my laptop to where my laptop can only do IPv6. Well, how's that laptop going to bring up the INE.com website or the Google.com website, which is running on an IPv4 only server, most likely? Well, that's where this particular feature could help you with that. So NAT64 primarily designed for that. Now, what if the reverse is true? What if I have an IPv4 only host that wants to connect to an IPv6 only server? Probably not going to run across that, but it's theoretically possible, and NAT64 can allow you to do that. So that's the third bullet point there. Mechanisms do allow the reverse connections to be true, from v4 initiating the connection to a destination v6 only host. And with NAT64, there are stateful and stateless versions, and I'm going to go into gory detail on both of those. As far as those two paragraphs of NAT64 were concerned in the official certification guide, they do want you to know everything I just mentioned. They do mention there the difference between stateful and stateless. Main thing that you'll want to know from that is that if I have v6 accessing v4 only, so if my v6 host is the initiator, if I primarily think that that's going to be the case, then stateless will work just great for me. Stateless works great when I've got a v6 connecting to a v4 only host. Now, if the reverse is true, if I expect that most of the connections are going to start from v4 only hosts and connect to v6 hosts, then I might want to use stateful instead. One of the other primary differences that you should be aware of is that with stateful NAT64, your v6 hosts can use whatever IPv6 prefix you want. Like you may have learned when you were looking at the 6-4 or ISOTAP videos that both 6-4 and ISOTAP, which were tunneling techniques, require that your v6 host have sort of predefined prefixes. Like 6-4 usually has an IPv6 prefix that starts out with 2002 in the first IPv6 word. Well, in NAT64, if you're using stateful NAT64, you can have any IPv6 prefix you want. Now, if you're using stateless NAT64, you are kind of restricted in how you're going to create your IPv6 prefixes. That really covers everything that was in those first two paragraphs of the official certification route guide for NAT64. Now, if like me, if you're a little bit curious about, hey, how are some of the details behind this? How does it actually work? Please continue on with me. If you don't care about that, you can stop the video right now, walk away from it, and be content that you just learned everything you need to know about NAT64 based on those two paragraphs in that book. So I'm going to go ahead and continue on with some more details, though, for those of you who want the details. So NAT64 relies on coexistence with DNS64. What is DNS64? DNS64 is this. Normally with a normal DNS server, we know that when I'm doing an IPv4 DNS resolution, what am I actually sending to that DNS server? I'm sending something called an A record lookup. If I do an A record lookup for google.com, actually in the DNS request it'll say A record, the letter A record for google.com. Well, when the DNS server gets that, he knows that A record means I'm trying to resolve that to an IPv4 address. If I send a quad A record, AAAA, 4 A's, then the DNS server, which must be a v6 DNS server, knows, okay, I now need the IPv6 address of google.com. So that's A versus quad A. Well, normally in a DNS server, whether it's running v4 or v6 or both, if I sent an A record for google.com, and if that DNS server looked it up and said, I don't see an IPv4 address for google.com, it would respond back to me saying, sorry, I got nothing for you. Now maybe that same DNS server actually does have a quad A entry for google.com. It actually has an IPv6 entry for that, but I didn't ask for that. My laptop asked for an A record. So normally that server would say, sorry, I've got nothing for you. In a DNS64 server, actually what he can do is if I send him, in this particular case, what is going to happen is the v6 host is going to say, hey, I need a quad A record for ine.com. Give me the IPv6 address for ine.com. Now let's say that ine.com actually has no IPv6 address. ine.com is a pure IPv4 only web server sitting in the IPv4 world. But here I am, a laptop running v6, and I'm querying my server saying, hey, can you give me the v6 address of ine.com? Well, in a normal DNS server, the server would respond back saying, sorry, I have no v6 address for you. But in a DNS64 server, something magical happens. That DNS64 server, when he gets a quad A lookup for ine.com, finds nothing. He says, I wonder if there's an IPv4, an A record for ine.com. So he looks over there and he says, aha, there it is. I've got an IPv4 only address. Oh, but the guy who made the request specifically asked me for an IPv6 address, and all I was able to find was an IPv4 address. I know what I'll do. I will take that IPv4 address and embed it, make it part of an IPv6 address. And so I will respond back with a quad A response as if I had an IPv6 address all the time for ine.com. The laptop doesn't need to know that what I'm actually giving him is an IPv6 address that was derived from an A record, an IPv4 address. And that is what a DNS64 server will do. It has this capability saying, couldn't find what you were looking for, found a different kind of address, so I'll convert that different kind of address into what you're looking for and reply back to you. And that's what's going on right here. Okay, so clearly these IPv6 addresses that will be created from what was originally an IPv4 address have to have a special format in order for that to happen. So basically what we're going to see here is that we're going to have a special IPv6 prefix, right, an IPv6 network that's going to be used for this kind of magic when we need to create an IPv6 address that has an embedded IPv4 address inside of it. The IPv6 prefix in front will be reserved. It will be known as a NAT64 prefix. Now there's two names for this prefix, and it's your choice as a network administrator which one you want to do. There's something called the well-known prefix. Now this is probably something you'd be tested on at the CCIE level. You're not going to be tested on this at the CCNP level. All this stuff I'm going into now is beyond those two paragraphs we saw in the official certification guide. So the well-known prefix is that one there in red, 64:FF9B, and that's a /96 prefix. Thank your lucky stars at the CCNP level. That's not a number you have to memorize. The well-known prefix. Or if you want, you can choose a network-specific prefix, which is anything you want. Your choice. It's probably a prefix you're going to get from your service provider. It's going to be a globally routable prefix, not some private prefix. But notice the two differences here. The well-known prefix has got a standard format. It's that number, 64:FF9B. It's a standard length, 96-bit prefix. So you can imagine, an IPv6 prefix is 128 bits long. So if I subtract 96 from that, what am I left with? 32 bits. I wonder what I'm going to put in those last 32 bits of the address. Guess what? It's going to be that IPv4 address of INE.com or Google.com or whatever it was that you were trying to look up. If I use a network-specific prefix, it can be anything I want from a /32 up to actually it could be up to a /96 if you wanted it to be, and you're still going to embed the IPv4 address at the very end of it. Actually, it's not going to be necessarily at the end of it. When you're using a network-specific prefix, and I'll show you this here on the next slide, the length of the prefix, whether it's a /32, a /48, whatever the length of the prefix is that you choose, that will determine where the IPv4 address gets put inside that whole 128-bit address. Let's take a look at that. So what we're talking about here is what's called an IPv4 embedded IPv6 address. And see, this is one of the critical things of NAT64, especially stateless NAT64. So what's that term stateless and stateful mean? In case you're not familiar with those, let me just do a quick high-level overview of that. Stateless means that nothing's keeping track of what you're doing. For example, this is in the IPv6 video series. Remember that in earlier videos, I talked about something called stateless automatic address configuration. Remember what that was? Stateless automatic address configuration was the idea that my laptop didn't even need a DHCP v6 server to obtain its own global IPv6 prefix and to obtain its default gateway. With stateless automatic address configuration, really what happened was the moment my laptop came up, derived a link local address for itself, what did it do? It sent out something called a router solicitation. It said, hey, is there any router on my link? I need to talk to you. If there was an IPv6 router, which there should be, the router sent back to me something called a router advertisement, where the router said, hey, here I am, I'm your router, and by the way, here's the global IPv6 prefix I've got in this link. Why don't you use this for yourself? And then my laptop could pick that up. Now it had a global prefix. It would dynamically derive the interface ID, and voila, without any DHCP involved whatsoever, I now had my IP information. Now we called that stateless because nobody was keeping track of that. The router has no idea, once he gave that router advertisement to me, if I actually used it or not. He has no idea what address I have. That address I've dynamically given myself has no lease time, or it doesn't expire at any particular point in time. Nobody's keeping state information. Whereas if you use DHCP, that is typically stateful, right? When I send a DHCP message to the DHCP server, he keeps track of me. He says, okay, I just allocated that MAC address, this particular IP address. I gave him a lease timer of 3 days. Now I'm going to keep track of that. So I can actually go into that DHCP server and see a listing of all the clients that have been allocated addresses and how long they're good for. Well, with NAT, there's also the concept in NAT64 of stateless and stateful NAT. In stateless NAT64, because we're using these special IPv6 addresses that have IPv4 embedded inside them, the NAT64 router doesn't need to keep track of anything. The address comes in, he says, oh, I need to translate this. All right, let me look right here. Here's the IPv4 address I'm going to use. Let me convert the header into IPv4 and send it out. And then the router goes, did I just do something? I don't remember. Did I just translate something? Oh, well, the router doesn't remember. He doesn't keep track of any of that. There's no NAT table that you can look at to see, oh, there's a translation entry right there. That would be stateful NAT. In stateful NAT, there's show IP NAT or show IPv6 NAT commands where you can see, oh, right now this translation has occurred. It happened 5 minutes ago. These many packets are using this translation entry. That's stateful information. NAT64, there is a stateful NAT64, but there's also a stateless NAT64. And if you're going to be doing stateless NAT64, you have to use these embedded addresses where the IPv4 address is part of the IPv6 address. So let's continue on with that. So as far as the IPv6 address is, here you go. Now let's go ahead and break this down a little bit. What exactly are we looking at? So what this is saying is, oops, let's go back here for a second. All right, well, this particular application I have here isn't running very well, so I'll just go ahead and cancel that. So what we're looking at here is it's showing you depending on the length of the prefix. So now we know that if you use the well-known prefix, that 64 colon whatever, that was a 96-bit prefix. And so that would be down here at the end. And that says if it's 96 bits, then you've only got 32 bits left. And that's where your v4 address is going to be. But if you don't use the well-known prefix and you choose, let's say you choose a 32-bit prefix. So your IPv6 prefix is 32 bits. Then the very next 32 bits is going to be your embedded IPv4 address. Then you've got a byte here, which is called the U octet. It's sometimes called the null octet. And this is just 8 bits of zeros. So the U octet is always zeroed out. And then you got the suffix, which is also reserved and also supposed to be all zeros. So in an IPv4 embedded IPv6 address, the way you would read this is, if my IPv6 address is, let's say, 48 bits long, then this is kind of weird. We actually take the IPv4 address and we split it in two. The first 16 bits of the IPv4 address go right after the prefix. Then we have 8 bits of zeros, our null octet or U octet. And then we have our remaining 16 bits of the IPv4 address followed by the suffix. So that's sort of how you read this chart right here. And this is saying, okay, if you're going to be creating embedded IPv4 addresses, it's got to follow these rules right here. And it all depends on the length of the IPv6 prefix as to where the IPv4 prefix will go after that. As you can see, it's probably easiest to have a 64-bit prefix where you've got your 64-bit prefix, 8 bits of zeros, your 32-bit IPv4 address goes immediately after that, and then you've got your suffix. Now, according to the RFC 6052, it says if you choose to have a 96-bit prefix, now you have to use this one, the well-known prefix. And then you won't have any kind of U octet or null octet, you won't have any suffix, and your IPv4 address will consume the remaining 32 bits of that address. Nothing you have to memorize or know for the CCNP, but in case you ever actually try to do this in your own network, this is how it works. NAT44, what's that? That's just regular good old IPv4 NAT. See, what we're talking about here is the 4 means I'm translating from a v4 header into a new v4 header. So your regular NAT that you learned at the CCNA level, where you swap your existing source address with a new source address, we call that NAT44. And NAT64 is where I'm swapping a v6 header for a v4 header. So what are some differences between them? Well, in NAT44, you had the concept of NAT inside and NAT outside interfaces, right? You had to go onto some interface and say IPNAT inside and another interface and say IPNAT outside. Well, NAT64, we don't have that concept. There's no such thing as inside and outside. You basically go to your interfaces that are going to be running NAT64 and you type in this command, NAT64 enable. Also, clearly what is being translated is different. In NAT44, we're only translating from one v4 address into another v4 address. In NAT64, we're actually completely swapping one protocol for another. All right, let's talk about stateless NAT64. This is kind of cool here. This is where we use those special embedded IPv4 addresses. Now the key thing here in Stateless NAT 64 is that the host that's going to have this embedded IPv4 to IPv6 address, it's going to have a static address. In other words, it's an address that doesn't change. This doesn't really work very well if you're trying to run this on a laptop where at any given moment that laptop is using DHCP v6 or something and his address is not predictable. It's got to be a predictable address on a predictable host. And notice this last bullet point here. This is the real benefit of using Stateless NAT 64. It allows bidirectional reachability. Either side can initiate the conversation. So let's walk through it here step by step. So step number one, you're going to get some sort of IPv4 global prefix. So like in this case, my service provider is saying, okay, for your entire company, you can have this class B, this 2.2/16. It's really actually a subnet of a class A, but you get the idea. Everything in your network can start with 2.2, and then I don't care what you do after that. Okay. Now we know that this is going to be embedded inside of my IPv6 address. So in this particular case, I've got two servers, server 1 and server 2, and I'm going to give them static addresses. And we know that server number 1 is going to be, we say, okay, here's what I'm going to do. I'm going to now subnet that and hang off router A here. All of their IPv6 addresses will have some IPv6 prefix. We don't know what it is yet. We don't see that. But then the IPv4 portion of that prefix will have 221. And this particular server will be 2211. And maybe there's another server hanging off of this same thing here that's 2212, maybe 22150, but everything hanging off router A will be 221. And everything hanging off router B will be 222. Okay, so I'm just doing simple IPv4 subnetting at this point. Next step, determine of my global IPv6 prefix, let's see here, determine the IPv6 prefix to be used with embedded IPv6 hosts. All right, so in this particular case, we're saying I'm going to use a /64. So 2001 : all zeros is going to be used for my embedded IPv6 addresses. Now let's put it together. Okay, so let's just take a particular host. If I know that all of my hosts are going to be doing NAT 64, I should say all of my hosts that will need to be translated, I know that they're all going to have the same IPv6 prefix. This goes a little bit against your logic because normally you would think, okay, if I go back to this diagram, you think, well, server number 1, because he's on one broadcast domain, should have an IPv6 prefix that's different than server number 2, right? Because they're not in the same broadcast domain, they're not in the same VLAN. What you're going to see here is they will end up having prefixes are different, but the first 64 bits are going to be the same. So server 1 and server 2, when we finally end up with their full IPv6 prefix, they will not have /64s. They'll have something bigger than that. But the first 64 bits will be the same on these two servers here. So we say, okay, all my servers are going to have the same 64 bits to start with. Then I've got to have, because I have a /64, we know that that says I've got to have the U octet or the null octet, which is 00, 8 bits of zeros. Then I put my v4 address in there. Now we know that all my v4 addresses start with 22 because that's what I got from my service provider. My service provider said all of your v4 domain starts with 2.2 and I don't care. First /16 bits. And then my suffix. So if we think about this, this is where the logical choice is to draw the actual subnet mask for the IPv6 address. So remember, every single VLAN needs a unique IPv6 prefix. Every broadcast domain needs a unique IPv6 prefix. Well, I couldn't have /64 because they all had the exact same 64 bits at the front end. So what makes them different? Well, their uoctet is all going to be the same. So they're all, every single VLAN in my IPv6 domain is going to have 2001.0.0.0. Then they're going to have 8 bits of zeros. Then they're all going to have 2.2. Where's my variation going to happen? Right here after the 2.2. So the next 8 bits in binary is where I'm going to have my variation. So for example, server 1 was going to be 221 something. Server number 2 was going to be 222 something. Server number 3 was going to be 223 something. So it makes sense that from an IPv6 perspective, I would put my subnet mask right here after the 3rd byte of the IPv4 address. So here we go. So server number 1 gets that address. Let's see if we can break this down one more time, because I know at this point in time it starts getting a little confusing. Okay, so server number 1. This portion right here is the IPv6 64-bit prefix that everybody gets. The first 64 bits are the same, 2001 and then all zeros. Now I know from an IPv4 perspective, everybody had to start with 2.2 because that was the /16 network I got from my service provider. So that's right here, 2.2. Everybody gets that. Okay, so it wouldn't make sense if I had my prefix right here. That wouldn't make a lot of sense, would it? That's 64 bits plus, what is that? Another 16 bits, so that would be 8 and 16. That wouldn't make sense because they're still all the same. From here to here, there's no differentiation in my bits. There's no way to tell one prefix from another. But now this server here is 221 something. So that's where I can draw my /96 right there. There is the 3rd byte of his IPv4 address. Here is the 3rd byte of the IPv4 address of server number 2. So that's where I can make my IPv6 prefix as a /96. I encourage you to pause this slide at this point if this part's a little confusing to you, and just stare at this for a moment and see how these addresses have been created for these servers. And remember, key point here, this server will always have this exact same address. This address has to be either statically configured on the server, or if he's doing DHCP, there has to be some mapping in the DHCP server that says, okay, when his MAC address comes to me, I will always give him the exact same IPv6 address. It has to be predictable. Okay, so router A right here, he says, okay, on this link, I know that I'm responsible for this prefix, this /96. And this router right here, he says on my interface, I'm responsible for this /96. So when they know that, now they have to use EIGRP v6 or OSPF v3 or something to advertise that prefix into the IPv6 network. So eventually, my NAT64 router, this is the guy right here. This is the guy that's actually going to be doing the translation of 6 to 4. He learns about those prefixes. He learns that those /96s exist out there and what interface they exist on, because A and B advertised it to him via some IPv6 IGP routing protocol. And now here's where we see our very first configuration commands. So notice there's no NAT inside or NAT outside. That doesn't exist. It's just NAT64 enable. So I do NAT64 enable on my interface leading to my v6 only cloud, and NAT64 enable on my interface leading to my v4 only network. NAT64 prefix stateless. So what this right here is good for is if this host right here, if he initiates a connection and what he's trying to reach is server number 1. Okay, well this host right here is going to do a DNS lookup. He's going to say, hey, DNS server, give me the A record, the IPv4 address of server1.ine.com or whatever. The DNS64 server is going to say, let's see here. I don't see an A record for that, but I do see a quad A record of this. Because I'm a DNS64 server, I know that I can take that, and because I've been told that the first 64 bits are the NAT64 prefix, I can ignore this portion right here, ignore that, and I now know that the IPv4 address is embedded right here. So the DNS64 will respond back to this guy saying, okay, you want the IPv4 address of server1.ine.com? It is 2211. So now this laptop, this PC, has just learned of an IPv4 address of server 1. And so he sends his packet. That's what this is right here. He's sending a packet to 2211, sourced from 1111. Now when that packet hits this interface, that interface has been enabled for NAT64. So he says, okay, if I receive an inbound packet on fast Ethernet 0/1, and the destination is 22 anything, and that's what this NAT64 route is. And he says, here's what I'm going to do. I'm going to route that packet to fast Ethernet 00. So I'll route it right here. And then I will convert it into an IPv6 header. And what I'll do is I'll take this address here, and in the front of it, add 2001:0000000. So as it leaves here, this NAT64 router has been able to convert the v4 address to a v6 address based on these two commands here. That's when the v4 host initiated the conversation. And here's how the DNS64 server would be configured for this. So there's the packet as it came in, and there's the packet as it leaves, as it's been translated. The v4 header has been removed. The v6 header has been applied. And also for this to work, you might be thinking, well, how is server 1 going to, when server 1 goes to reply to this, when he goes to reply this direction, this will be the destination of the packet, right? When server 1 goes to reply back. Well, when that IPv6 packet hits router A, how's router A going to know what to do with that? Well, presumably, the NAT64 router, which is also doing EIGRP v6 or OSPF v3 or RIP or something, initially, he advertised a route into this cloud that looked like this. Hey, everybody, if you need to get to 2001:/64, send your packets to me. So this router says, oh, okay, I know about a whole bunch of /96s. I know about this /96. I know about this /96. But when I get this packet here, that doesn't match those, but it will match this sort of generic, less specific route. This is sort of like a summary route. saying if you need to get to anything that starts with the first 64 bits are 2001:0000000, and you don't have a more specific route to match, send your packets to me. So that will allow router A to respond back and get those packets back to the NAT64 translator. So that was stateless NAT64. And noticed no state information maintained on the translator itself at all. The only NAT configuration was right here. No NAT state tables, no static translations configured. It was all based on simply the knowledge of what prefix is being used for translation, what interface, if I get v4 packets and I need to send them into the v6 cloud, which interface am I going to send them to? And that was it. Really, no, on this NAT translator right now, there's really no show NAT commands to see what information has been translated because he's not keeping track of that. There's no state. Now let's contrast that with stateful, where the router obviously will maintain session state. Why would we do this? Why are we adding this extra burden to the router? Because the plus side, or the positive to this, is right here. Hosts do not need embedded IPv4 addresses. That whole thing that we just went to that said, okay, let's see, if I use a /32 IPv6 prefix, I need the null octet here, I need the 32 bits of the IPv4 address there, I need to structure it in this special way. Don't have to worry about that. With stateful NAT64, you can use any IPv6 prefixes you want on your hosts. Now here's the one downside of NAT64 if you use it with stateful. It's only good if your IPv6 hosts will be initiating conversations with the IPv4 hosts. It does not work the other way. This is like normal NAT, right? Normal NAT, you've got an inside and an outside. And only hosts on the inside can initiate conversations to hosts on the outside. Same thing is true here. With stateful NAT, there's no way for the v4 host to start the conversation. So let's just go ahead and take a look at this. Remember what NSP stood for? Network Specific Prefix. Basically just an IP, it's just a fancy way of saying, what's your IPv6 prefix? What's the global IPv6 prefix that my company has been allocated? This is just another way of saying that same thing. It's called your Network Specific Prefix. So in this particular case, our service provider has given us a /48, and we know that of that /48, we're actually going to subnet that out into /64s, and that'll give us something like roughly 65,000 /64s we can come up with from this one /48. And of those 65,000 /64s, we're going to use one of them for NAT64. So this one that we see right here. This is the specific /64 that we're going to use for NAT64. Okay, so the NAT64 router using OSPF v3 or EIGRP v6 or whatever, he's going to send an IGP update saying, hey everybody in the v6 cloud, if you need to get to this specific /64, you can get there through me. So now all the routers in the cloud know that. And notice in this particular example right here, here's another /64 ending with :F that we're using. So we're using :1, that's reserved for NAT64, and then :2, :3, :4, all the way up to :FFFF. Those other 65,534 combinations we can use in this cloud over here. Via DNS64, so this is no different. The hosts say, hey, give me the quad A record, the IPv6 record for example.com. Well, example.com doesn't have a quad A record. He's IPv4 only. So the DNS64 says, okay, let's see, I was only able to find 1111. Let me prepend to that the network specific prefix that has been reserved for NAT64, and that gets me this address. So the address here, the part of this in green was his IPv4 address. The part in red is a network specific prefix that we've tacked on to the front of it. And that's what he responds back with. And so here is the IPv6 packet as it reaches the NAT64 router. And then the NAT64 router with this wonderful configuration right here is able to translate it into an IPv4 header as it goes out. A little bit more complicated we can see on the router side in this particular case. If we break down these configuration commands, if you're curious. So once it comes into Fast Ethernet 00, several things happen. Step number one, the packet has to arrive on an interface that's been enabled for NAT64. It has, so that passes. Step number two, when the router looks at the packet, he looks at the destination address. He says, okay, let me do a comparison here. I know that if this packet's going to be translated, the first 64 bits of the destination need to match this pattern. Do they? Oh yes, they do. That's a match. So that means this is a packet that needs translation. Let's say it didn't match. What if the destination address was 2001:ABCD:FFFF:something? He'd say, well, it came in on a NAT64 enabled interface, but the destination address is not my stateful prefix, so I will just route this via normal IPv6 routing. He would just attempt to route it via his normal IPv6 routing table. In this case, though, we're okay. The destination actually is our specific NAT64 prefix. Great. Now he says, okay, now let me check the source address of this packet. I'm only going to translate packets if they match the access list called test. Here's the access list called test, which says I will only translate packets if they came from this /48. Well, sure enough, the first 48 bits of the source address do match that. It says, okay, great. I am allowed to translate this packet. So the destination matched what I was looking for. The source matched my ACL, so I'm allowed to translate it. So what's he going to do? He says, okay, well, I'm going to strip off the IPv6 address, and I'm going to replace it with a new IPv4 address that I pull or I obtain from the NAT64 pool that's called INE, just a named pool. And that pool says, okay, you can pull an address from 2232 all the way up to 22320. And if all those addresses are already used in current translations, overload it. Start doing port address translation.